It's a fun diagram. Okay, so let's try this problem. So we have two mixtilinear incircles. And we draw the circumcircle and the incenter. So okay, so we need to draw, let's draw the midpoints of those arcs and mixtilinear incircles. So here's usually how I like to do it. There's a couple different ways to draw the mixtilinear incircles, but let me think about this. So basically we take this point and this point and draw the intersections of them with the arcs. Let me just make this a little smaller. So these are going to be where it's tangent. Oh, why did I draw BI? I meant to draw BI. So these are going to be where they're tangent. And also, let's draw these. So this point is the midpoint of this arc. And now I'm just confused. Wait, so this is one of the points of tangent C, and this is the other point of tangent C up there, right? And I think so I should draw GF and GE, and this will give me the two mixtilinear. So these should not be collinear in general. These, but here's a mixtilinear incircle. It should be this, this, and that. Wait, that doesn't make sense. This. Oh no. It needs to be the midpoint of this arc. Okay, let me hide a bunch of stuff. Confusing myself. Okay, I'm just gonna hide a whole bunch of stuff. This... All right. Forgot what point F is, but it should be points G and H. I'll leave B and E there, but we need to take the midpoints of these arcs, and if I connect G to both of them, I think that should be the mixtilinear incircle. So I need to take this circle. There we go. That's better. And then for H, I'm gonna hide this, hide this. So F is the midpoint of one of the arcs, and and I want to do H. Oops, how did that go away? What just happened? I want H and this point and this point. There we go. Okay. And those are the two mixed linear incircles. And it took a long time to do it, but I did it. So, all right. So we have, this is WB, this is WC. Okay, so this is B1. And this is C1. And B2, C2 are opposite of B and C, are the antipodes. Okay, so we want to draw the center of ABC. So we should get a rectangle, I believe, right? So when we reflect them about those points, this should be B2. And so B1, C1, B2, C2 is a rectangle. I think it is. And we want the intersection of B1, C2 and B2, C1. Maybe it's not a rectangle. So the points opposite of B and C on omega. So maybe they just mean the center of the circle. Wait, B1, C2. That doesn't make sense to me. Should be the antipode of B, not. Oh, you're right. That's my bad. So this should be B2. And this should be C2. And that will make a rectangle, but so this here is a rectangle. And we want to let B1, C2 intersect B2, C1. So let me shrink the figure a little bit so that we can see the intersection. There we go. And that's X. It doesn't look like XA equals XI, so maybe I drew something wrong. B1, C2, and B2, C1. So this, I switched the names of B1 and C1. This should really be B1. And this should be C1. And I should kind of intersect internally. So, okay, so B1, C2, B2, C1. And that should be X. It's a hard figure to draw, kind of, but I think that's good. So this is X, and we want to show XA equals XI. One sec, I'll be right back. All right, thanks for waiting. So yeah, this is a really weird problem. Let's see if there's anything special about the circle. Does it pass through? No, I don't think so. So C1I and D are collinear, where D is like the midpoint of arc ACB. And similarly, these are collinear. And this is collinear. This is collinear. We have a lot of stuff. This looks like we might want to use Pascal. And we have this, and we have this. So yeah, plenty of collinearities. Also, it's the same as saying that X lies on JM, right? Because JM we know is the perpendicular bisector of AI. So maybe somehow we can use Pascal's theorem. Maybe we could show that X lies on the radical axis of these two circles, because that would be equivalent. Kind of like that idea. But yeah, we just have to figure out how do we find the power of X with respect to this circle. Maybe draw the line XI or something. It's a good problem though. Yeah, of course we also have this and this. So yeah, a lot of lines in this figure. Maybe Pappus or something? Is X, I, and O collinear? That looks like they might be. Yes. So that we could try to prove. Is that just Pascal's theorem? I'm not sure if it's that easy or not. I think it might just be Pascal's theorem on C1, C2B, and CB2, B1. Yeah. Well, actually, maybe not, because these two intersect at O. These two intersect at X, but C1 and B1. Okay, so we know that Pascal says OI and G are collinear. And then maybe we could show GX. So C1, C2B. Yeah, can we just use Pascal? Let's see. I feel like if we use Pascal enough times, it might do it, but I should think about it a little bit more. Actually, I think Pascal shows that X, O, and G are collinear. Then we need to show that I, G, and O are collinear. So maybe we can introduce points M and J. Because what if we have MEF, CDJ? So if we do MEF, CDJ, so MC and JE meet at O. MC and JE meet at O. And then we have MC and JB. So maybe it's MBE, JCD. But then we would need to add this point. So I think this point should also lie on that line. Oh, maybe it's just a symmetric argument, because maybe, I wonder if, yeah. Is X just a reflection of, so X is not a reflection of H over O, but I think we can like show that these are collinear. And then maybe somehow we could use like C1BE and B1CD. Because then that would show that G, I, and H are, yeah, we need to involve B2 and C2. So if we have C1, C2B and B1, B2C, then that would show that X, O, and G. Like I feel like Pascal enough times should show that those are collinear. I almost just want to assume it for now. So yeah, I'm going to write down the whole thing. So then we would want to show that these are collinear. So maybe we could use like Pascal in reverse or something. So yeah, I think it's very likely that we just use Pascal enough times and that solves it. So let's write this out. I'm going to write it on a piece of paper first. So we have C1, C2B, and then B1, B2C. This would imply X, O, and G. So we can show X, O, and G are collinear. And then we have C1MB and B1JC. That implies okay. I feel like I'm adding even more points, but this would also line that line. So yeah, how do I draw it? This point right here. P. That would imply that P PI, probably making this harder than I need to. P1G, that means that PG and PG and I are collinear. And then we have MC2B and JB2C. That implies IO and I think there's like even another point. So where these intersect with this. Q. So I have IO Q. I'm missing something here. I need so I have HO. Yeah, now I'm just drawing a million lines. You know that HO, you know that this also lies on that. HO and R. What am I missing here? And then R. So C2B2E and C2BE and B2CD means that HO and R are collinear. I'm missing one. And then what if I do MBE and JCD? So if I do MBE and JCD, that would give that HO and I are collinear. Okay, so I have HOIQR. I can show that HOIQ and R are collinear. That still doesn't show that X is on it though. But I need one more with point G. So I think C1MB. I know I already did that one. C1MC2 and B1JB2. I think that might be it. C1MC2, B1JB2. So that means that PQ and X, no, PQ PQ and X are collinear. I'm getting so close. I just so I can show H, O, R, I, and Q are collinear, and I can show P, Q, and X are collinear. And P, G, and I are collinear. And X, O, and G. Oh, you know what? I think I got it. So H, O. No, I almost got it, but I didn't. I need one more Pascal. So I think I got to use E and F or D and E again. So ABC1ME and B1JD. I think that might work. So if I do C1ME and B1JD, that means that P so ME and JD meet at O. And then C1D, yes, I think this is it. C1D and B1E meet at I. So PO and I are collinear. Okay, so I've used, let me see how many times I need to use Pascal. 1, 2, 1, 2, 3, 4. And then we know P and I are collinear. And then this shows that G lies on it. This shows that X lies on it. And this shows that G lies on it. So X, ultimately we want to show what? X, O, and I are collinear. So I can show X, O, and I are collinear by doing Pascal's 1, 2, 3, 4, 5 times. I don't know if it needed to be that hard, but I got it eventually. So let's just assume X, O, and I are collinear. Okay. Oh, actually, I can do it with just 3 Pascals. So by just doing Pascals 3 times, I can show that. In fact, I don't need point G. I'm going to get rid of point G. Make things easier. And I don't need point H. So I'm going to get rid of that. But I do need P the way I did it. Where's point Q? Did I have a point Q somewhere? Oh, okay. So I did need that point Q. I need this to do my proof. Whoops. Because I show that I, O, and Q are collinear. And then I show that P, O, and I are collinear. And then I show that P, Q, and X are collinear. So I show IOX, IOQ are collinear, and then IOQ, IOP, and then PQX. Okay, see you next time. All right. So XA, we want to show equals XI. So let's see if we can use Pascal's again. So X, so let's say C2 M C2 E MC2E so wait. So we want to show X as the intersection of MJ and B1C2. So MC2E, B1J, and B1JD. Okay, so this would imply, so we have MJ and B1C2. We want to show that's X. But MB and B1E, then I'd have to create a new point here. And then C2D. Yeah, I don't think I want to do that because I'd want to show that X, this point, and this point are collinear. Okay, so let me change it around. MC2. Let's try BJC or B1JC. Let's try that because then it would be MC. Yeah, B1JC. So this would imply. So MC and B1E is I. And then CC2 and EB1. So hold on a sec. So JM and B1C2. And then CM and B1E. And then CC2 and JE is O. Okay, all right, I proved it. I solved the problem. Okay, so this is fun. All right, I don't need this O1, but actually, what was that circle for? Oh, that's like a tangency point. So I'll say label the points as shown. You just use Pascal's enough times and then it solves it. 4 times. So first by Pascal on MC2B, JB2C, I, O, and Q are collinear. By Pascal on, I'm just going to type them all up and then you can look them over. On C1, MC2, B1, JB2, P, Q, and X are collinear. By Pascal on C1, ME, B1, JB. We have P, O, and I are collinear. And then this means that I, O, and X are collinear. And then we use it one more time. So by Pascal on MC2E, B1JC. Then we have MJ intersect C2B1, I and O are collinear. And that means that X equals MJ C2 B1. And that implies X lies on JM. But by the in-center external lemma, JM is the perpendicular bisector of AI. And so that implies that XA equals XI. I'm so proud of myself because I'm always afraid to use Pascal and I'm always afraid to use inversion, but I'm conquering my fear. So let's see if this proof is right. So we have MC2B and JB2C. So those would be the points Q, O, and I. Okay. And then we have C1, M, C2, and B1, J, B2. So that would be P, X, and Q. And then we have C1, M, E, and B1, J, D. So that would be P, O, C1, M, E, B1, J, D. That would be P, O, and I. Yes. So if you combine all these, that means P, O, I, Q, and X have to be collinear. And then we do this. Isn't that fun? You like that solution? All right, let's move on to the next problem.
Yeah.
Yeah, it's fun. All right, so let's see, we have a couple more. Let's try this one. Let's do that for next time. I just don't want to because yeah, I have the app right here, but I just want to spend the rest of the time just solving problems. And then next time I'll make the tools. I promise you next time I'll make the tools, and then we could do it a lot faster.
Yeah, okay, it's okay.
So altitude AD. So H is the orthocenter. So first I'll draw the altitude. Actually, you know what? I'll just do this. Just going to reflect this over, and that'll be H. So that's the orthocenter. So this is H. And M is the midpoint of BC. D prime is the reflection of D over M. Okay. P is on D prime H, such that AP and BC are parallel. So this is P. And the circumcircles of AHP and BHC. So the circumcircle BHC is like the reflection of this circumcircle ABC over BC. So these meet at point G. And we want to show MHG is 90 degrees. So this problem doesn't look like it should be that hard. It looks like it looks kind of easy. So let's see if that's true or not. But yeah, it's hard to tell. Okay. So we want to show MHG is 90. We know PGH is 90, so that's kind of the same as showing that MH is parallel to PG. And I wonder if I did this already on my YouTube channel. So I think this looks a little familiar. So like if F is the midpoint of AP, then like these triangles are similar. So MH and F are collinear. And we want to show, HF and PG are parallel. It's a good way to do that. I wonder if PG and D are collinear. No. So yeah, we really don't need point D. Well, we kind of need point D prime because we need to know this line, D prime H. So what if I draw this? So basically, I think this will pass through the center of the circle. So yeah, I don't know if it's worth drawing the antipode of H, and then we try to show that those are collinear. draw the center of the circle. Let's call this O. Let's call this Q. So HM, we know HM passes through the antipode of A, right? We know that. So F, H, M, and A prime should be collinear. So HD equals DE and AF equals FP. I don't know if we can use that somehow. It should be parallel. So we want the antipode of H, which is this point, and not the midpoint. We want the antipode. So that should be collinear with these. So we have this and this. And we want to show that all these are all collinear. Well, actually, I think we kind of know these are. I wonder if this is obvious. Yeah, it is kind of obvious because, yeah, like once we know that these are all collinear, yeah, in fact, we really just need that A prime, M, and H are collinear. I don't know if we need point F. But I feel like this diagram kind of makes it look obvious. Because, yeah, we know that this is 90 and we know that this is 90. So, yeah, the last step is basically, it's really not a hard problem. Okay, so let's type it up. So let H prime be the antipode of H and BHC. And let A prime and H prime be the antipodes of A and H. And BHC and ABC. Oh, I thought this line passed through D. It doesn't, so maybe it's not as easy as I thought. I got confused. I thought it looked like these passed through D, and then it looked like the problem was really easy. But let's see. Maybe it's still not that hard. Like we know these are collinear. Yeah, the question is how to show that this is parallel. So we know HM and A are collinear. And maybe I do need point F. Maybe I'll add that back in. because then we know that we want to show HF is parallel to GP. And yeah, because AO equals OA prime, so we know FO is parallel to PA prime. I wonder if that helps us really. Oh, we just want to show A prime, A, M, and H prime are collinear, and M is the midpoint of AH, but that's true. Like, yeah, so it is an easy problem. Because so ABH prime C is a parallelogram. That's like a well-known fact. So yeah. So that implies that M is the midpoint of AH. And then so let F be the midpoint of AP. Do we need point F? I'm just thinking if we actually really need it. I think we might. Yeah, we need point F. Oh, or we could say ADH prime D is a parallelogram. So that would mean, yeah, I'm wondering if we could just get rid of point F. No, I don't think we can just get rid of point F. So let F be the midpoint of AP. Since so HDD prime is similar to HAF, sorry, HAP, so F, H, M, and A prime are collinear. So HDD prime HAP. So that means that F, H, and M are collinear. And so AF equals FP and AM equals MH prime. So first of all, angle PGH equals 90 and angle HGH prime equals 90. So they're collinear. All right. And AF equals FP, AM equals MH prime. And that means that MH is parallel to HG prime, H prime G. That solves the problem. So yeah, I think everything got proved. I don't think there's anything missing here. It's possible there's a way to shorten it, but I'm not so sure there is. Yeah, I think that's really the way to go. So yeah, let's move on to the next one. So we have two of them. One involves like a 60-degree angle. Let's try this one. So we have triangle ABC. H is the orthocenter and O is the circumcenter. Okay. P is the midpoint of AH. T is on BC, so that angle TAO is 90. That's kind of interesting. Let's draw a couple things. So if P is the midpoint of AH, then it's going to be the center of the circle. And so TAO equals 90. Let's draw perpendicular. And this is probably where the tools are going to help us next time. So I think this line is parallel to EF, right? So I'm going to draw DEF, DEF, G, and I believe this line where TAO equals 90 is tangent. So we know it's tangent to the circle because OA is a radius. And I'll just draw this because why not? Okay. And now I can hide a whole bunch of things. So 1, 2, 3, 4, 5, 6. Right? And this and this. All right. Okay, so X is the foot of the altitude from O to the line PT. That's interesting. And yeah, I could use the foot of the altitude tool. I'll do that on the next session. Okay. So this is X. And we want to show the midpoint of PX lies on the 9-point circle. So that's J. Let's see the best way to draw this. Okay. So this is cyclic. P is the center of that. So we want to show that DFJE is cyclic. And it looks like P, well, we know P lies on a 9-point circle. So we know D, F, P, and E are cyclic. You just need to show J lies on it. That's interesting. So maybe it's worth drawing the midpoint of BC, and we can call it M. And then we have OX. I think we have a circle through 5 points. OAX, M, and T. Because we have all those right angles. So that might be helpful. So we know OT is like a diameter of this circle. So the center of this circle will be the midpoint of OT. And I wonder if KI is perpendicular to BC. I think it is. Maybe not. Yeah, it's not true. Okay. Let me move things a little bit because X almost looks like it lies on AC. So maybe, yeah, I don't want X to look like it lies on AC, but I also don't want T to be too far away. So let's see. I think that's okay. Maybe just shrink it a tiny bit. Whoops. All right. Let's see what time it is. We have about 20 minutes left. So we have the J is the midpoint of PX and P is the midpoint of AH. I wonder if, I would be very surprised about this, but I wonder if JM is perpendicular to TP. Let's see. I don't think that can be true because I think MX is perpendicular. Wait a sec. Oh, is that really true? So, okay, so basically it looks like MJ and A are collinear. Is that obvious? Or would that solve the problem? If MJ and A are collinear. And not only that, that's very interesting. So that makes me think, I wonder if BPXC is cyclic. No. I'm surprised that, so basically we want to show AM and TP are perpendicular. I think that might be obvious because I think P is like the orthocenter of AMT. Okay, so I think it might not be that hard to prove that those are collinear and perpendicular. So first of all, P is the center of this circle, and M is the center of this circle. So MP is perpendicular to EF. And we want to show MJ is perpendicular to PJ. So But if we know MP is perpendicular to EF, and EF is parallel to AT, so MP is perpendicular to AT, and so P is like the orthocenter of ATM. And so we know that those are perpendicular. And to show that J is the midpoint, we would need to show angle PMB PMJ is XMJ. Well, this is a right angle, and J is the midpoint of PX. So I think, but we know, okay, we know it's perpendicular, but how do we know? So like if we let J prime be where AM and PT meet, we know it's perpendicular. How do we know it's the midpoint?
It is obvious because X is the, sorry, P is the orthocenter, right?
X,
And X lies on the circle. So X would be the reflection.
you're right. Yeah, because the reflection of the orthocenter lies on the circle. So yeah, so that proves that this is all true. So then we know that, we know that AM and TX intersect at the midpoint of PX. Okay. And so now we just want to show that that lies on this circle. And we know that all those points lie on it. So can we just use power of a point? Can we, because AP times AD, then it's obvious because we know PJDM is cyclic. So we've solved the problem. That was too easy. Oh wait, we know PJDM is cyclic. But it might be a different circle than DEF, right?
PDM is the 9-point circle, right?
Yeah, you're right. So yeah, that solves it because PD and M we know lies on it. That was like too easy. Okay, I did not expect that it would be that easy. All right, so I will type it up. Okay, so first we could call this J prime. So we could say let AJ and TX, let AM and TX intersect at J prime. And then angle XAT, so X is the perpendicular from O to PT. So angle OXT is OAT is OMT is 90. So OXATM is cyclic. And then MP, so M is the center of BFEC and P is the center of EFEH. And that means that MP is perpendicular to EF. And that means that MP is perpendicular to AT. And that implies that P is the ortho center of ATM. that implies that Pj prime equals J prime X. Did I miss something? Let me think about this. I think that's right. Implies J prime equals J. Wonder if there's like one step I'm missing, because so did we show that, so X is the perpendicular from O to PT? Okay, so AM. I think we're okay. And then JPDM is cyclic. PD and M lie on the 9-point circle. And then JPDM is cyclic, lies X lies on the 9-point circle. All right. I think that should be everything. So a little easier than I expected. I did not expect that we would solve all these problems. So here's the last one. We could just draw it. It's like a 60-degree angle problem. And I could probably draw a tool for this later. I'm going to want to do rotate about 0.60. And this will be C. E and F are the theta angle bisectors. So those two angle bisectors should make an angle of 160. Or sorry, 120. I've seen this before. So this is cyclic, this quadrilateral right here. So here's the incenter. And this should be E and F. And this should be cyclic. And PEF and QEF are equilateral. That's kind of interesting. So I can do that like this. Actually, that should just be this point right here. So this should be P, because this would be 60-degree angle. And then the reflection of P over EF. I feel like I might have done this, something like this on my YouTube channel before. And I think we used like Pythagoras a whole bunch of times. So if I reflect, but I don't think I've done this exact problem. So P, and that's Q. Oh yeah, I think the problem was like to show that Q lies on BC. I think that's like well known, although I don't remember the proof, so we could try to prove it. So O is the circumcenter of APQ. And we want to show OI is perpendicular to BC. Oh, and it looks like O lies on EF, so GeoGebra is helping us a lot here. Let's make it look nicer. right. So I don't think BFEC is cyclic. Maybe we can make this a little bigger. So yeah, first of all, is it obvious that Q lies on BC? I think I've done something like this on my channel before. I don't remember the proof though. I wonder if BQ equals, I think that might be the proof. So I think it might be that BF equals BQ and CQ equals CE. Because, yeah, that has to be the proof. Because I think these two are both kites right here. Like you can reflect F across IB, and you can reflect E across IC. And then I think an angle chase, like an angle chase shows that these two add up to 180. And so if you reflect them across IB and IC, they would be at the same point. And so that proves that and it has to be an equilateral triangle because by symmetry, because of the reflection, EF is equal to EQ. Because yeah, you're really reflecting triangle BFE, like the whole triangle along the angle bisector. So EF equals EQ, and because this is a kite, and similarly EF equals FQ, so that's equilateral, and then P would be the reflection of Q over that. So these should be collinear because let's think about that. So by an so this is isosceles FIE because angle IFE is IAE and IEF is IAF. So since this is isosceles, by symmetry, we're going to have QI and P are collinear. And now we want to show OI is perpendicular to BC. I think this might be easy because I think these might be isogonal because we know this is perpendicular to EF. Yeah, QI is perpendicular to EF. And we want to show OI is perpendicular to BC. Actually, let me check if that's true. EIO and DIF. I don't think it is true. Yeah, I got too excited there. Yeah, because this is 60 degrees and this is left. Yeah, no, that can't be true. So let's think about this. We could try to show IB squared minus IC squared is OB squared minus OC squared. It's one way to try it. Maybe OI is the perpendicular bisector of that, of GQ. So looks like it is. Oh, it has to be actually because PGQ is a right angle. Because since this is an angle I think we can probably show that PQ's. Oh, actually, I don't think that is true. I was wondering if PQ's a diameter. No, PQ's not a diameter because O is a center. But So is this actually a perpendicular bisector? Because if it was, I don't think it actually is. Let's see. Oh, it looks like it is. Interesting. So, yeah, so I don't know why that would be a perpendicular bisector. Okay, so is it obvious that, so OG equals OQ? Oh yeah, it has to be if it's perpendicular. So we need to show IG equals IQ. That would solve it. And I wonder if that's just like true by symmetry somehow. So we want to show IG equals IQ. You know what? What if, let's draw the incircle. So basically, if we draw we want to show, it's the same as showing that GH equals HQ. Sorry. Close. And we know that BH equals BJ, and we know that CH equals CK. And we know that I think that proves, well, let's see, BH equals BJ, and BQ equals BF. So it's the same as showing that FJ equals KE. That would solve the problem. And that's the same as saying that, okay, so we want to show FJ equals KE. Let's see. Oh, we're almost out of time. I think we're really close. Let's see. So here we have KE, and here we have FJ. I think that might be bashable, because AJ equals AK. Yeah, because AJ is equal to AK. And then to find AF, it's kind of like using the angle bisector theorem, and same with AE. So, I mean, basically, we want to show AF plus AE is twice AJ, and that seems like it's probably solvable. In fact, maybe even Ptolemy would work with that, because AF times IE plus AE times IF, that's the same as AF plus AE times IF, would be EF times AI. So I would bet that if we use Ptolemy, we could show that AJ plus AK, or AE plus AF is 2AJ. Actually, I think it's even easier than that. It's because triangles IJF and IKE are congruent. I think that solves it. And then we know that FJ equals KE, and that proves that GH equals HQ, and that proves that OI is perpendicular to BC. So yeah, that is the solution. We're out of time, so I'm not going to type it up. But yeah, we solved all the Elmo problems. I'm very, very proud of all of us. So yeah, I think I'm going to stop here. But for everyone watching on YouTube, thanks for watching. If you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again, and have a great day.